Hello.
Hi guys.
Welcome to the course on rethinking texture mapping. I guess we can start. So let me start with this. Back in 2008, when I publicly started talking about an alternative to texture mapping, people were looking at me as if I was crazy. How can you even think about this, right? I don't believe it's the sentiment today. I think people are more open to the idea of reconsidering texture mapping because it has some really serious problems, and we're going to go over that. So my name is Cem Yüksel. I'm from University of Utah. My collaborators for this course is Marco and Sylvain. Sylvain is not with us today, so Marco and I will talk about all sorts of different techniques. There were proposed either some significant improvements over texture mapping or complete alternatives to texture mapping. So this course is all about going over all these different techniques that what we say are rethinking texture mapping. We are not going to, now I'm going to repeat this a few times because it's important. We are not going to explain each and every method to its full detail so you can go and implement it. This is not what this course is all about. This course is about the fact that there are many methods that are proposed as complete alternatives to texture mapping. And they all have their advantages, they all have their limitations. And they offer different things. So for a specific application, what would be the ideal method to replace texture mapping? And I think you should replace texture mapping. But picking the ideal method requires some thinking, right? In this course, we're going to give you the information that you will need to find out what method would be ideal for your particular application, right? So what we're going to do is that we're going to go over all these methods at a high level, just give you a high-level understanding of how they work, and then we're going to go through the evaluation that we had about each and every method. We're going to talk about their advantages, we're going to talk about their disadvantages, so that you can compare and contrast and figure out what works for you, right? I'm going to repeat this, I guess, a few times. Let's start. Let's start with, I guess, texture mapping itself. So texture mapping, as we all know, is the fundamental means by which we define some high-frequency details. Typically, it's color on a given surface. Well, we have this digital surface, and we have some texture. And they typically live in different spaces, right? So we have a model space, and we have a texture space, and we have a mapping in between. And you'll see that a lot of the problems are related to this mapping in between. And many of these methods will try to either modify this mapping or get rid of it or replace it with something substantially different. One problem with that is actually there are quite a few problems. One obvious problem is that this mapping, if you have a relatively complex model, this mapping would include some seams. That is, you start with chopping up your model into pieces and flattening it over the surface, right? This is a labor-intensive process as well. And this labor, because it's labor-intensive, if you go back and you realize, oh, I needed to modify my model in some way, I may have to redo this mapping, right? So this makes the modeling iterations quite complicated. Or if you realize, oh, wait a minute, I need more resolution at some point, you may have to go back and change your mapping, right? These are significant problems because the mapping process is not fully automated. Can it be fully automated? Not really, because that involves some artistic decisions in practice. Okay, we have these seams, now we have this mapping. Are we done? Well, these seams introduce other problems. So this is not just about authoring, but there are also rendering-related problems. These seams would introduce seam artifacts by linear filtering. You can hide them, maybe, but this is you see those black lines on this character. When you go to MIPMAP levels, they're going to be a little more prominent. So if you were to hide them, what you need to do is that you'll need to paint around the seams so that you don't see this black background, but you see a color that is kind of closer to what it should be. So that it is possible to maybe hide them, but unfortunately it's not possible to completely get rid of them. Nonetheless, they may not be too visible, and that's the practice, right? But if you generate a bitmap from this texture, you're going to start seeing it again, right? They again show up at bitmap levels because our bitmap levels actually are not correct. They're generated from this texture that includes information from different parts of the model. So when you build a bitmap pyramid, you don't get the correct bitmap pyramid that represents the correct filtering. But if you don't use bitmaps, typically, well, if you don't use bitmaps, maybe if your texture has some high frequency details, it might be possible to get away with. And this is typically what we do in practice for hiding the issues with texture mapping. Nonetheless, if you don't use texture maps for colors, if you use it for other things, for example, displacement maps, then things become a lot more complicated because any inaccuracy that you have along the seam that you cannot theoretically completely get rid of would mean cracks on the surface, right? So this is a lot more difficult to hide. So you need to be very, very careful about where you place your seams if you're doing displacement mapping. Another thing that happens is that now that we have seams, even if your model does not have separate pieces, your texture map will have separate pieces. That means along the seams, you will need to duplicate your vertex data in the texture map. So a particular vertex can have two separate texture map coordinates, right? Depending on which face they're associated with. So in this case, for example, we were looking at a part of the model, and there's a seam that goes through it. So all the vertices along the seam have duplicated texture coordinate data. And that complicates things a little bit. Another thing is that texture maps are not tessellation independent. So if you have a different tessellation of your mesh, you may have to redo your texture mapping. So LOD becomes a little bit of a problem. Well, we have to acknowledge that there has been quite a lot of efforts on automating this mapping process because, you know, we keep going back to the problem of mapping and how labor intensive it is. And there are quite a few methods that actually try to help with this process. What we're not going to do in this course is that we're not going to talk about these methods at all. They do definitely help, and we must acknowledge that. Nonetheless, they do not provide a complete replacement to the manual mapping process. And at the end of the day, you still have a texture map, right? Even if you automatically generate your mapping, you still have a texture map, and you're still living with the problems of seams, and that's fundamental to texture mapping. So if you were to summarize the problems of texture mapping, there's definitely a problem of defining a mapping, which is labor intensive, cannot be fully automated, it's time consuming, even for experts. And for novice users, it's almost, it's not something they want to start, right? Back when I was learning about computer graphics, this is one thing that scared me the most. I really didn't want to do this. I still, to this day, try to avoid it as much as I can. Local resolution adjustment is problematic. We talked about this. Model editing after texture painting is also problematic. So because of that, this modeling iterations becomes a big problem, right? So you can't just prepare a model, paint it, and edit your model concurrently at the same time. What you have to do is that you need to finish preparing your model. You need to say that I'm done with modeling, and then you can go to your painting. And when you do your mapping, you better be sure that your mapping is correct. So that complicates the iterations quite a bit in practice. And also, they introduce, even if you're happy with your mapping, they introduce seam artifacts in rendering. There are also additional storage costs, right? We have duplicating vertex data, but also we are not perfectly packing our color information in texture space. We need to put some space between different pieces, and that adds some storage cost as well. And, of course, there's mesh dependency. You do your mapping for a particular mesh, and it may not work for a different tessellation of your map. So as I said, there are quite a few methods out there. Quite a few researchers thought about this problem, and they offered different solutions to it. And this is what this course is all about. We're going to go over all of these techniques. So as Marco was suggesting me to say, this is a little bit of an extended fast forward. We're going to talk about these methods. We're going to have about 5 minutes per method. So don't expect us, again, to explain each method in full detail so that you can go and implement it directly. But we're going to try to provide enough information so you know what those methods are, you know what their benefits and disadvantages. To be more detailed, this is our course outline. We're going to try to follow this timing as closely as we can. We group these different techniques. We loosely group them. They may not perfectly fit in their group, but it kind of makes sense. We're going to start with methods that are very much like traditional texture mapping, but they sort of fix some of their problems. And then we're going to talk about connectivity-based representations. These are probably the most widely known ones. Sparse volumetric textures are using volumetric structures. We're going to talk about those. And then volume-based parameterizations, going back to UV mapping, but defining it in a different way. And in the end, we're going to have conclusions and questions. So we're going to defer all the questions towards the very end so that we make sure that we have enough time to talk about all of these methods. Now, our evaluation is probably the most important part of it, so I'm going to go through about how we're going to evaluate these methods. So we have these 5 categories. We're going to talk about its applicability, usability, filtering quality, performance, and implementation use. And we're going to have this score sheet for each method, right? As you see, they all have different subheadings. Let's go over them really quickly. For applicability, we're going to see if they can be used for meshes. Well, they better be used for meshes, right? Because that's what we're typically using. But other things we might consider are point clouds, implicit surfaces. Are there any shape and topology limits enforced by the method? Can they handle subdivisions, or do they give us tessellation independence, right? These are important things that we may consider. So if you look at standard texture mapping in this context, yes, you can apply them for polygonal meshes. With point clouds, they're not great, but you can use them. With implicit surfaces, that becomes a little bit of a problem. There are no shape and topology limits. You can have arbitrary subdivisions of your mesh after you do the mapping, but they're not tessellation independent, right? So as you see, there's some coloring involved in here. Typically, green means good, red means bad, and yellow is sort of dubious. It could be interpreted as good or bad depending on the application. So Sylvie, Mark, and I had long discussions about how to color these things and how to evaluate each method. So we did not come up with these evaluations lightly. They were results of very, very long discussions. Well, some of them were easy, but some of them were kind of difficult. So I would like you to take these as like more like a suggestion rather than the ground truth. So this is these are the evaluations that the 3 of us agreed upon. But some of them are a little more questionable. So we're not going in depth for each and every one of them. So this is applicability. We have usability. So this is about how you would generate the texture map and what kind of problems you might have with it. Is there automated mapping? Is it good enough? Manual mapping, can you do it, or do you want to do it at all? Model editing after painting, is that even possible? Resolution readjustment, which is something important. If you realize that you need more resolution at some point, can you do that? Or you realize, oh, you actually didn't need that much resolution at some point. Can you go back and reduce your resolution locally? Can you have texture repetition? Can I take a texture of something and repeat it all over the model? Can I have a 2D image representation so I can use my existing 2D image editing tools, right? With standard texture maps, automated mapping methods do exist, but they do not fully solve this problem, right? Because there is some artistic decisions involved. So you often need some manual intervention. Model editing after painting is definitely a big problem, and resolution readjustment, again, is a big problem. On the other hand, if I want to take a little texture and repeat it over the model, that's fairly easy to do. And at the end of the day, we have a 2D texture representation, so we can use our 2D editing tools. So those are great. Filtering quality, minification filtering, magnification filtering, anisotropic filtering. Is that possible, and do we have any problems? With texture mapping, yes. So this is something that a lot of people don't quite realize. We assume that, oh yeah, all these things work because they're designed for 2D texture maps. Yes, but the way we use texture maps introduce seams, and as long as you have seams, you have seam artifacts with magnification filtering, minification filtering. We even have incorrect bitmap levels, right? And isotropic filtering, yes, again, seams introduce seam artifacts. So these are not so great with standard texture maps. Performance. Are there any storage overhead or vertex data duplication? Is there any access overhead to texture data? Is there any computation overhead, or is hardware texture filtering is possible? Well, the 2D texture maps overall score pretty well in this front because, hey, our system is designed for these, right? So they better perform well. Yes, we have vertex data duplication, and we were storing 2D texture coordinate, and there's some wasted space, but it's not too bad. We don't have any access overhead. We can directly access the texture data using the UV coordinates. We have no computation overhead, and yes, we can use hardware texture filtering because it's built for that. In terms of implementation, here what we're thinking about is how difficult would it be for you guys to go and switch to a new alternative to texture mapping in your pipeline. So we're going to talk about in two categories. We have this asset production. How difficult it is to develop the necessary tools for asset production, and how difficult it would be to develop the tools for rendering. With standard 2D texture mapping, well, there isn't really anything because we're already using it. So we already made that investment. We have all the tools that we need, so there's no problem there, right? So we're going to look at these methods as a full score sheet, right? This is a score sheet for standard 2D textures. And you see that we highlighted some of them with stars. So typically, when we show a slide like this, we will go over the ones that are marked as stars. So star doesn't mean good or bad. Anything can have a star next to it. That means that these are important points about this method, and these are the points that we're going to highlight while we're discussing that method. Now, this is the full score sheet for standard 2D textures. All right, so this was a specific technique for some specific problems. This is a more general technique that I'm going to talk about, seamless texture atlases. This is the whole process. It kind of looks complicated maybe, but it's not all that complicated actually. So it starts with what the authors call quadrangulation. So you take your model and you chop it up into pieces again, but those pieces have sort of approximate quadrilateral shapes. We want that because we would like to take each one of these charts, each of these pieces, and flatten them into a square-shaped region on the texture map, as seen like this. So these square-shaped pieces or charts are packed into a texture. And there are different ways of handling bitmaps with this method. They can be stored within the same texture, but they will introduce one extra overhead. That is, you need to store a lookup table for your texture mapping, such that you need to know where to go, which part of the texture map to read. So each chart will treat as if they're a complete separate texture, but they're going to be stored in this one texture that contains everything, and we just need to know what part of that texture to read. If you want to make use of hardware bitmap storage, you can actually do that. You can pack your bitmaps differently, and in that case, you're going to have a different type of lookup table stored. Another thing to think about here is that your charts will need to have half a texel boundary, so that when you're doing texture filtering, you're not combining the colors between different charts, right? So they're going to be contained within their own region. This means that when you have MIPMAP levels, when you have different resolutions for the same chart, you need to adjust your UVs. You need to scale them such that they still have this half a texel boundary in between, right? And you might also notice that that the way that the charts scale because of this boundary requirement is a little non-traditional. So from 7 texels to 3 texels to 1 texel. So it's not like powers of 2, but nonetheless, it still provides good filtering quality. And the advantage is that we can use hardware bilinear filtering using this method. However, we need to have an indirection, right, using that lookup table. That would have some performance constraints, of course. And it will require quadrangulation and automated mapping per chart. So there's going to be, you could say that the mapping part is automated. However, you will have some difficulty controlling your UV mapping. So this is what the score sheet looks like. I want to start with the filtering quality part. So it's solving the problems of magnification and minification filtering with a little bit of a different MIPMAP construction. On the other hand, in usability, it helps maybe a little bit, but the automated mapping is still going to have the problems that we're familiar with from 2D textures. And manual mapping in this case is extra difficult because you're going to have to obey some extra constraints, right? So it's solving some of the problems of texture mapping, but unfortunately not all. So these were the methods that looked at texture mapping sort of within the same context with some improvements. Our next section is about methods that start with, nope, this is not the one, that use the connectivity-based representations that already do exist in our meshes. And they're going to rely on that for texture mapping. Perhaps the most widely known method of this type is PTEX, right? PTEX is actually a very simple idea. At first, it kind of sounds crazy, but it totally makes sense. The idea is to have a separate texture map for each quad-shaped face. Yes, a separate texture map for each face. At first, if you're not familiar with this method, you could say, whoa, this isn't too much. Well, you're going to adjust your resolution accordingly. So in the end, it works just fine. So if you have a quad-shaped face, this is how you would place your texels. So you don't have to worry about UV mapping at all because each one of your quads that already do exist in your mesh representation will have their own texture map, right? What becomes a little tricky here, unfortunately, is that filtering near the edges, this is that gray area near that face that I highlighted, would require accessing the colors of the neighboring faces, right? So you can filter across the edges. So that part becomes a little tricky because then you need to know what those faces are and you need to be able to access those colors. That means you need to store an adjacency list. So this is showing an example of an adjacency list for a very simple model that includes 4 quad-shaped polygons. So it's not just, this adjacency list is not just recording what the neighboring face is, but also which edge of the neighboring face corresponds to this particular edge that I'm filtering across, right? But as long as you have this information in your shader, you can access those colors and do the filtering properly. One additional difficulty here, which is kind of not immediately obvious, is that if you have different resolutions, which you can have different resolutions on different faces, which is great, right? You can adjust your resolution locally. But if you do have different resolutions, then filtering across the edge becomes a little more tricky. So you need to do a lot more to make sure that you're not going to get seams across the edge. And in some cases, it might be actually quite tricky. Triangles can be handled in this context. I thought this was a brilliant way of handling triangles. It's a little unusual. You still need to pack them as quads, as if they're quads. But there's a way to do that. You're basically picking the alt texels and flipping on the other side and packing them as if they're colors of a quad, but they're actually colors of a triangle. So in texture filtering, you kind of need to be a little careful. Am I filtering a quad? Am I filtering a triangle? But as long as you're careful, actually, you can use this. So I thought it was a brilliant way of packing these colors for quads, triangles, sorry. These extraordinary vertices become a little problematic, right? If you assume that all vertices are valence 4, that is, they're neighbor to 4 faces, things become a lot easier. But the vertices are shared less than 4 or more than 4 faces, then you're going to have these what we call extraordinary faces, extraordinary vertices. I'm sorry, and filtering across them becomes a problem. So you may need to get you may get some filtering artifacts. You may have a seam at one point on your surface. Well, do you care? Do you not care? You may not care too much because the seam is now concentrated around a single point on the surface, right? So maybe it's not too big of a deal. And in practice, I believe a lot of people will argue that it is okay. So this is the score sheet for PTEX. What's really important here is the usability. So if you look at usability, we have all these green stuff now. We don't need mapping. We don't need to define a mapping at all, right? We can directly use our model, which is great. So we eliminated this one really labor-intensive component of our texture mapping process. And on top of that, it allows us to edit our model after painting. And it allows us to locally adjust the texture resolution wherever we want. Well, what we gave up in the end is, maybe picking a small piece of texture and repeating over the model might be a little bit of a problem because we don't really have a UV parameterization now. And our 2D image representation might be a little undesirable. Because we're not going to have, well, we can still have a 2D image representation. It's just going to be lots of colors from different pieces of the model. It may not look as pretty as we would like. So you may not want to work with existing 2D image painting tools with PTEX. You may want to use a 3D painting tool instead. On the other hand, in terms of filtering quality, it's great. Yes, there are some maybe issues with extraordinary vertices, but if you ignore that, the filtering quality is great, so you can have really high quality filtering. However, now you have some additional performance costs, right? You need to store this adjacency list, and you need to send it to your shader. And your shader will need to access your topology information so that you can filter across edges. So that creates some indirections because you need to know the adjacency information while you're filtering. And also, you need to do some custom filtering to this, and you can't really rely on hardware texture filtering with PTEX. In terms of implementation, that has some cost as well. You want to have a 3D texture painting tool, and in terms of rendering, you would want to write those custom shaders that will handle PTEX. Right? There's another method called mesh colors that I personally like a lot. So this is actually very, very similar to PTEX. It came around the same time, actually. And the way mesh colors work, the way I like to explain it is, you can think of it as an extension of vertex colors, right? In fact, the lowest resolution mesh colors would be vertex colors itself. So in this case, on the very left, you see that vertex colors are defined on a triangle. So if you want to know the color at any point on that triangle, you can just linearly interpolate those colors. With mesh colors, you can have higher resolutions. With one higher resolution, you're going to have colors exactly at the centers of the edges. If one higher resolution, you're going to have face colors along with edge colors as well. And you can have any arbitrary resolution that you want, right? Again, just like PTEX, there's really no need for UV mapping. So how does it compare to PTEX? It's actually very, very similar. The only difference is the way that the colors are placed. So in PTEX, you place the colors inside a face. With mesh colors, you place your colors along the edges and exactly on the vertices. And this seemingly minor difference actually has some practical consequences. So we talked about this, right? With PTEX, as you get close to an edge, you will need to access the colors of the neighboring faces. With mesh colors, you get rid of that dependency. You just need to know your edge colors and vertex colors. So the information about a particular face can be self-contained. So by doing so, you still need custom texture filtering, but you will not have this indirect lookups, and you won't need to store an adjacency list. And you won't have any problems with extraordinary vertices because any vertex will have its own vertex colors, right? There's no ambiguity about what the color of that particular vertex should be. So if you look at the score sheet for mesh colors, again, you'll see it looks very similar to PTEX. We have all these usability improvements, such as model editing after painting and resolution readjustment, and absolutely there's no need for worrying about texture mapping at all. But again, 2D image representation is not going to be as pretty as we used to have with 2D textures. In terms of filtering quality, it's great, right? It has no problems with filtering. Everything works just fine. You just need to have your custom filtering operations. In terms of performance, it's also good. In terms of storage, it's good. You won't have this additional adjacency list, and you just need to store your face resolutions, right? And there's no access overhead. You can directly access your colors without having to go through a lookup table first. But you're going to have custom texture filtering. And you cannot rely on your existing GPU texture filtering hardware. On top of that, in terms of implementation, again, you will need to have a 3D painting tool if you want to take full advantage of mesh colors. And for rendering, you need to implement your own custom shaders. Now, this hardware filtering, you may care about it, you may not care about it, but if you're doing real-time rendering, you better care about it, because hardware texture filtering is known to be about up to an order of magnitude faster than doing this in software. Even if you're implementing it on the GPU, if you're writing your custom texture filtering code, it may run a lot slower than using the existing texture filtering hardware. So for that, we have mesh color textures. So mesh color textures, the whole point is combining the advantages of mesh colors and providing a form of using the hardware texture filtering unit. This is a very new method. Actually, I presented it 3 days ago at HPG. So let's talk about briefly how it works. The idea behind it, the main idea, is sort of obvious, right? GPUs don't understand mesh colors. They are designed for filtering 2D textures. If you want to use mesh colors on the GPU using the existing texture filtering hardware, you kind of need to pack mesh colors as if they are 2D textures. So they convert mesh colors to 2D textures, right? Naively doing this would duplicate the vertex and edge colors, which is not too bad, but this can be minimized. So if you have neighboring faces sharing edge colors and vertex colors, you can just place them together so you won't have that duplicated data. And you need to be a little careful about diagonally placed edges. You need to make sure that texture filtering would give you the correct result, but that can be handled very, very easily. You can have mip-map levels, just like regular 2D textures. However, those mip-map levels will need to be stored separately because the resolution of those mip-map levels will not follow our power of two progression of regular 2D textures. And hardware will not allow you to arbitrarily customize the resolution of your mip-map levels, so you're going to need to store them separately. This means that you're going to have to sample your mip-map levels independently and interpolate them. The problem here, the non-tricky component of this, non-trivial component of this method is how are you going to handle the UV mapping across these different mip-map levels that have sort of different resolutions, right? One important point here is that with mesh color textures, you need to be sure that your vertices are placed on the UV map exactly at the centers of some texels. And you need to make sure that this is the case for any given mipmap level. This means that I need to have a different UV coordinate specified for each mipmap level. So if you were to store all these all these UV coordinates for all mipmap levels, that's going to require a ton of storage. To get rid of that, to handle that, instead what we're doing with mesh color textures is that we're storing a 4D texture coordinate. This 4D texture coordinate has two components, two 2D coordinates, and using this really simple math over there, you can compute the 2D texture coordinate for any given mipmap level. So all these UV coordinates for all mipmap levels are packed into just one 4D coordinate, right? And as long as you have this one 4D coordinate, you can compute the UV coordinate for any given mipmap level. And I'm not explaining how it's done. As I said, we're not going to dive into details, but it is actually explained in detail in the Mesh Colors texture paper. So the advantage here is that now we can use hardware texture filtering. And as I said, mipmap levels are stored separately in separate textures, so that means that you need to have two texture calls instead of a single texture call. But in terms of performance, this doesn't make a difference because your two texture calls will use bilinear interpolation, not trilinear interpolation, right? So if you were to use regular standard 2D texture maps, you could get away with a single texture map call, but then single texture map call would look at different mipmap levels and then do the trilinear interpolation. So it's going to be a lot more of an expensive texture lookup. These two texture lookups will be a lot cheaper because they're just doing bilinear texture filtering. And indeed, if you look at computation overhead, it's really, really minimal. You just need to figure out what mipmap level you need and convert 4D texture to 4D texture coordinate to a 2D texture and just linearly interpolate the results of two texture lookups. What I'm not showing on this slide is the measurements I had for the performance overhead. For new graphics hardware, if you compare mesh color textures to standard 2D textures, the performance overhead you're paying, the cost is about 0.01 milliseconds on average. So I'm talking about 10 microseconds here, which I think is something that we can afford. So what you get here is pretty much the benefits of mesh colors, right? We have all these usability benefits of mesh colors. And we have the filtering quality of mesh colors, except I must highlight here, is that when anisotropic filtering, you can use anisotropic filtering, but you're going to get seam artifacts. Because these are not mesh colors anymore, right? We moved from mesh colors to 2D texture land, and as long as we move to 2D texture land, we're going to have to pay something for it. That is the cost of anisotropic filtering showing our seams. Again, just like 2D texture maps, there is vertex duplication. The storage overhead is a little more, perhaps, because now we're not storing just 2D texture coordinates, we're storing 4D texture coordinates, right? But on the other hand, we have no access overhead. We have our computation overhead is really, really, really minimal, negligible completely, I would say. And we can use the hardware texture filtering. In terms of implementation, the rendering part of it is really simple, right? And what you need to do for modifying your texture is really simple. But for asset production, it would be ideal if you were to rely on mesh colors themselves, and it would be ideal if you use a 3D painting tool. You can still make use of mesh color textures using existing asset production pipeline, and that would give you some benefits, definitely, at least in terms of filtering quality. I'm not going to go over them, but if you're really interested in using mesh color textures and you're really worried about having a 3D texture painting tool, feel free to come and talk to me, and I'll tell you how you can immediately use your existing production pipeline for mesh color textures. So these are the connectivity-based representations that were proposed as alternatives to texture mapping. Now we're going to go directly into sparse volume textures that are proposed as alternatives to texture mapping. So what's the problem? If I'm going to have a volumetric representation of my texture data, then as my resolution increases, the storage will increase with the cube of that resolution, right, which is really bad. But I don't really need to store all the colors in the volume. I just need to store the colors in the volume that would correspond to the surface that I'm trying to paint, right? So we can make use of that sparsity. And this is what these methods are going to do. So I'm going to start talking about first with adaptive texture maps. That's not quite using volumes per se, but it has a very similar ideas. And then octree textures and Ancube trees or brick maps and gigavoxels are just going to be different ways of exploiting that sparsity. In this context, we also have spatial hashing that will use a different way of, again, packing that sparse data. So let's start talking about with adaptive texture maps. The idea is very, very simple. Let's say that you have this 2D texture, and you are not really making use of your entire 2D texture. You see this texture that is called original here. A significant portion of that texture, as you see, is allocated to just background color. As you know, this is the color that you are not really using, right? So this is like the wasted space in your regular 2D texture maps. The idea here is to minimize that wasted space by packing your texture slightly differently. So we can get rid of the storage for this background color that we actually don't need. So with smooth regions with less detail can be eliminated. And so your texture map will be stored in will take up less memory. That's the idea. And I'm talking about this because if you look at the score sheet, you could say, well, what am I getting out of this? This is used in special cases where you're going to have lots of background, right? But the advantage of this is that the reason why we're talking about this idea trivially extends to 3D, and it kind of is very related to 3D stuff that I'm going to talk about in a minute. In terms of usability, this is still, it starts with a regular 2D texture map, so it doesn't provide too much improvement, but it allows us to dynamically adjust the resolution locally. Well, it's not like you can adjust the resolution of any given face independently, but still it gives you some amount of local resolution adjustment. And since it's using this 2D textures, you have the benefits of 2D texture representation, although you're sort of giving up your nice 2D image representation that you had with 2D textures. In terms of filtering quality, it has magnification filtering, minification filtering, but you have some typical CM artifacts, right? You're going to pay the cost of indirection in terms of performance. There is that as well. But in terms of implementation, it's very, very simple, right? You can take your existing 2D texturing pipeline and start using adaptive texture maps fairly easily. Let's talk about volumetric structures now. Well, octrees is one of them. So this is basically storing the colors in an octree structure, obviously. And the nice thing about this is that you're kind of storing your MIP maps along with your sparse data structure. So it will start, let's say this is the highest level of your octree representation, and I want to know the color at some point within that volume. So I'm going to start with, so like you see on the right side, we have the representation of this octree on the GPU texture memory. So I need to know what quadrant of that octree that point of that node that point corresponds to, and from that I can follow the pointers to go to the next octree level, right? I find that next octree level, and then I follow the pointer to the next one until I leave the leaf node, and that leaf node will store the color. So that would require a number of indirections until you reach the color that you need. But nonetheless, it gives you a sparse representation. Well, this idea can be generalized using brick maps or n-cube trees. It's basically the same idea, but you would say that an oak tree would split a cube into 8 pieces, right? And because of that, you may need quite a few indirections until you reach your data. So you may have a little bit of a deep tree, if you will. If you want to have a shallower tree, that would mean that you can get to your final color value with fewer number of indirections. You can split your volume into more pieces than 8. And that would bring us to brick maps and n-cube trees. So that's the idea. So in this case, you won't be able to exploit the sparsity of your data as well as you would with an oak tree. But in the end, you will have a shallower tree. That means you're going to have fewer number of indirections. So this is going to give you some performance benefits in terms of computation. But the cost is perhaps a little more storage, right? And GigaVoxels is using the same idea as well for representing sparse data with very, very large content. So if you look at these n-cube trees and brick maps, what are the advantages? Well, we can handle polygonal meshes because there are some surfaces in 3D. But now we can really efficiently handle point clouds, and we can even have texture filtering with point clouds, yes. Because it's really that these representations are oblivious to how the surface is defined. As long as there is something in space, we can represent color on them. And implicit surfaces, they're perfectly fine. If you're using implicit surfaces, volumetric representations are actually great for that. The one problem, however, is that there's a bit of a shape limitation here. If you have thin features that are on the order of your texel sizes, or voxel sizes, then you may have some inconsistencies in terms of coloring, right? You better have enough voxel resolution to represent your thin features, right? So your texture representation is not only dependent on the frequency of the texture information that you're storing. It also depends on the frequency of your model detail. So that's what you need to be careful about. But in the end, subdivisions are fine. Tessellation independence, you could think that, whoa, I would have tessellation independence, that would be great. Actually, yes, but you kind of need to be a little careful because a different tessellation of the mesh may not have exactly the same surface. And if you don't exactly have the same surface, your surface may not be exactly in the same position in 3D space. And if you're not in the correct place in 3D space, you may not be able to access your colors at all. Or you may end up accessing the wrong colors. You kind of need to be a little careful about tessellation. But in theory, it is possible as long as you're careful. In terms of usability, again, we completely got rid of mapping and all the issues with mapping. We have model editing after painting. Yes, you can say, oh, I modified my model. How am I going to preserve my colors? Well, the part that you modify is not going to preserve their colors, but the rest of your model will preserve their colors, so that's good. And we have local resolution adjustment with these tree structures. You can say a part of that model will have more and more resolution. You can handle that easily. But obviously, we don't have the 2D texture representation anymore. They can handle magnification filtering and minification filtering. Anisotropic filtering becomes an issue. It's really difficult, if possible at all, to define anisotropic filtering with volumetric structures because you could say, you could assume that you're on a plane and you're going to filter across this plane, but as you're filtering across the plane in 3D space, you may actually end up at some place where there's no color information at all, right? So this anisotropic filtering becomes really, really tricky with these methods. And obviously, there are some performance overheads with lots of dependency, multiple lookups. So performance is not going to be great, but they're still usable, right? So they're not ridiculously slow. It's just that you're paying the cost of some performance overhead. And in asset production and rendering, you're going to have to do some work as well. You can't rely on 2D painting tools. You have to do all your painting in 3D, and you need to have your custom shaders. So a lot of the problems in terms of performance comes from the fact that we have this hierarchical structure, and we will need to go through multiple levels of the hierarchy to access our color data. The question is, can we do better? The answer is yes, by using a hash function. So if I had a hash function, I can use my hash function directly with one indirection to directly go to my color data. So instead of going through the hierarchy of some volumetric structure, I can use this hash function to directly access my data. So this is showing an example in 2D and using a hash function here. And with a typical hash function, you can say a hash table will have lots of empty space, right? But if you try to optimize your hash function, and you can do that, you can have a fairly compact representation of your colors without much space in hash space, right? And you can avoid the fact that 2 points in space can correspond to the same position in that in the hash space by picking just the right hash function. So picking the right hash function will be the complicated part of this process, but as long as you have the right hash function, you will get some performance benefits. And in theory, this would require about 1.4 n bits, so it can be quite compact, but in practice, you might need to store a little more data than your colors. And the way that we're going to access the colors is that we're going to have this offset table, right? So for a given position, we're going to, instead of computing a complicated hash function, we're just going to store this offset table. So we're just going to look up whatever that table value is. This will allow us to use pretty much any hash function. So your hash function does not have to have a mathematical description. It can be just a lookup table, right? That's the idea. And with that lookup table, obviously, it's going to, multiple points in our 2D space in this example will correspond to the same point in our hashed offset table. That means they're going to go to the same position in the hash table, right? So that means they're all going to have the same color. Not quite. We're going to use we're going to add a little bit to that hash value based on where that pixel is, which repetition of that hash offset that pixel location is. If you add that together with the value that you get from your hash table, you're going to go to a different position in our hash table, and we're going to get a unique color for that position. And you need to make sure that you're not going to have any collisions. Well, in theory, this is possible. You just need to be a little careful. And in the end, you can have efficient SIMD execution, and it doesn't really require that many GPU operations. You're just going to have a little bit of extra bits, and you're going to have this one indirection. That's going to be your cost. So I talked about this in the context of 2D. This tree really extends to 3D. In this case, you're going to have a 3D hash table and a 3D offset table. Filtering, however, becomes something that you need to be a little bit careful about. With bilinear filtering, you can do multiple textual lookups and then do the filtering yourself. With MIP mapping, you need to store your MIP map levels. Well, one way to do that is to take all of your MIP map levels and put them in one image, right? Since we're going to represent this in a sparse data structure, it doesn't really matter if you place your MIP maps in whether you place your MIP maps in the same context, right? You can put them all together, and this gray, supposedly wasted space won't really show up in your storage. So you're perfectly fine. The difficulty, however, is the multiple accesses. So that's going to make the filtering process a little complicated. because if you want to know the color at this point P, you need to read these multiple points. And of course, it's going to be a little more slower in 3D. One way to get over that is using what they call blocking. So instead of storing a single color value, I can store the colors of a block. So if I'm storing the colors of a block, then I can go and read that block data from my hash table instead of that color data. So with a single evaluation and with bilinear filtering, we can even make use of the texture filtering hardware at that point. We can get the interpolated colors. But the cost that I'm paying for is that now I need to store blocks for each hash location. That means I'm going to have to store a lot more data, right? There's going to be a lot of data duplication, right? But it helps with your filtering process. So if you pay the cost of extra storage, you can get some performance benefits. So if you were to compare the data for a block size of 2 with mid-maps, is in this case that uses space of 77 megabytes. If you don't have any blocking, you can have 17 megabytes. So it's whether or not you want to have blocking is, I would say that it's sort of application dependent, right? Depends on what you want to do with these. So what do we get out of spatial hashing? Well, we can support all sorts of different surface types, right? We can have, again, just like any other volumetric structure, pretty much anything is possible. But again, we have the same limitation of shape. So your thin features, you kind of need to be careful about your thin features to make sure that your resolution of your hash table is high enough to handle the thin features that you might have with your models. Again, subdivisions are perfectly fine. Tessellation independence is, we have the same problem, maybe even a little more, because you have the full resolution hash table at any point. So you need to make sure that your different tessellations of your surface will have the exact same final 3D surface in the end. As long as you have that, you can have tessellation independence. But that's quite a bit of a restriction, I would say. We have, of course, automated there. Well, there's really no need for mapping, so you have that usability improvement. However, now that we don't have that hierarchy, model editing after painting becomes a little bit of a different story, because now you need to recompute your hash table from scratch, right? So that complicates model editing quite a bit. Although you can still preserve your colors, so maybe it's partially okay, but you need to do your hash table computation from scratch. Resolution readjustment is not something that we can have. We're going to have full resolution everywhere. And of course, we don't have the 2D texture representation. But in the end, we can have magnification filtering, minification filtering. Anisotropic filtering, again, is not something we can handle with volume-based representations. We don't have vertex data duplication in terms of performance, but we're going to have some storage overhead, right? Actually, a significant storage overhead if you're using blocking. Without blocking, it's actually fairly okay, acceptable perhaps. We have access overhead. We have this single indirection overhead, but it's much better than other volume-based representations, so you might prefer the perfect spatial hashing because of that. And obviously, there's some computation overhead. And in the asset production, rendering is simpler with single indirection with blocking. If you're not using blocking, then you will need to do your linear filtering as well, so it becomes a little more complicated. You'll need to have a custom shader, right? So these are the volume-based representations that we decided to cover. But Marco and I will be here. We'll be happy to answer your questions. I'm hoping that the question is not going to be which method is the best one, because as you might have seen, it really depends on your application, and maybe it depends on who you're asking. If you're asking me, I'm going to say mesh colors, but anyhow, we're going to be here. We're going to be very, very happy to answer your questions. So please come down here and talk to us. Thank you.